Hello, class. Okay, so started a question in class. I just kind of picked a random question from the book and then realized that we didn't kind of cover something that we needed. So I want to start up by just covering a little background, and then we'll do this problem. So let me start by reading the problem. It says, an argon ion laser produces a cylindrical beam of light whose average power is 0.75 watts. How much energy is contained in a 2.5 meter, let me write that down, length of the beam? So we have this beam of light with a length L and a cross section A, which we are not given. So to start out, let's review intensity of light. So when light, or just electromagnetic waves in general, whatever type they are, but when light hits a surface, and we're really considering this case of a normal incidence. So the light is hitting it parallel to the normal vector. And again, it's not difficult if we consider a different angle, but we don't need to right now, so let's not bother with that. All right, so the question is like, how much energy is delivered to this surface? And that depends on both the light and the surface that we're hitting. And so we isolate the property of the light itself. Like, use an example, like you have a light in a room, and say you have a nearby surface, there's a certain amount of energy being delivered to that surface. But if you change the light bulb and make it brighter, more energy will be delivered to that surface. So we define intensity to be the property of the light itself, and we use the letter S for intensity. It's measured in watts per meter squared is the basic SI unit. Okay, so we define intensity as power over area. So like the amount of energy delivered to this surface will depend on time. So if we take, instead of energy, if we take power, which is energy over time, we remove time as a factor. And of course, a bigger area will catch more radiation. So if we divide by the area, that removes a surface from as being a factor. So, just why we define intensity the way that we do. Okay. So that's intensity, how we define it. So let's look at, let's look at this laser beam here. We can say the intensity is the power over this cross-section area. And there's kind of a nice way we can relate this to energy density. So let's say that this beam of light has a length L. So if you consider a photon at the left end, in a time delta t, it'll travel. Let me just write this down and then explain it. We can say the length of this beam of light is the speed of light times time. Because this is just the distance that photon will travel in a time t. So, like every photon that starts out here is going to reach, like if we put a surface here, let's say that the end of this beam is where we're hitting a wall. It's like any photon here is going to hit the wall in this time interval t, or anything in between here. Photon outside won't quite make it. So we can write the volume of this cylinder as ACT. Okay. Now, power is energy over time. So we can say now, we always have to be careful when we're dealing with this topic Because, if I write E over AT, that might look like electric field. So I'm actually going to write out energy over AT. Okay. Now, just so we don't mix it up with the electric field. Now, let's take this equation here. I'm just going to rewrite it algebraically. Just by moving terms around. So if we divide by AT, we have V over AT equals C, and then we divide by V and get it like this. So here we have energy, 1 over AT times energy. So this 1 over AT in front, that's C times V times energy. And then here, energy over volume is energy density. So let's write that down. Energy density is energy over volume. And so we get this nice relation here that the intensity of light is, we have a relation between the intensity of the light and its energy density. So let me write that down over here. S equals CU. So S is intensity, C is the speed of light, and U is the energy density. So a nice relation between them. Okay, so now that we've got this done, let's go back to this problem where we have a laser, and we want to know how much energy is contained in this portion of the laser. So let's start with this relation we just derived. So the intensity is the speed of light times the energy density. And energy density, I'll just write out energy over V for volume. And just like before, the volume is A times L. So, we're not calling it ACT in this case because we're actually given the length of the beam. So, what I want to do now is let's multiply both sides of this equation by A. So we have S times A is equal to C times energy divided by L. And the intensity times the area is the power. So we have power equals C times energy over L. And, the energy is just the energy contained in this beam. That's what we're trying to solve for. So let's write that down. So the energy contained in this laser, that would be the power times the length over the speed of light. So again, I'm going to do I'm going to write this as 7.5 over 10, so 0.75 watts. The length is 2.5 meters, and then we divide by 3 times 10 to the 8th meters per second. And let's throw on a watt is a joule per second. So we can say a joule is a watt times a second. And just going over the units, let's just do that off to the side. Watts, meters, seconds, and joules. On the bottom, meters, watts, and seconds. So we get our energy in joules. And then all we have to do is plug in the numbers. What I'm going to do is I'm going to say 10 to the 9th nanojoules is equal to a joule. So if we clean this up a little bit, we have 7.5 times 2.5. Oh wait, divided by 3. And let's just check that. I think that's right though. So, here 10 times 10 to the 8th is 10 to the 9th. So that's going to cancel. Yeah, all we have left as far as numbers are just 7.5, 2.5, and 3. So, just, let's see. That's going to be around 6 nanojoules. So, not much energy stored in this, this laser, but kind of expected. It's less than a watt. I mean, a normal light bulb is 60 watts, so this is not the brightest light. Okay, so yeah, I wanted to do a question in class about energy density, so yeah, just had to push it back because I realized we hadn't gone over this part yet. But yeah, I'll stop here. So yeah, I guess that's it for this problem.